Hi, everybody. So it's my great pleasure to be here and to talk about machine learning as a service. By the way, how can I close this? Maybe how can I make it disappear? No, but I want to. Okay. Sorry. This one. Okay. Okay. So So my name is Shou-De Lin, and I'm a Chief Machine Learning Scientist of Appier, and I'm also a professor in National Taiwan University Computer Science Department. And today I'm going to share about machine learning as a service, and I'd like to discuss some challenges and opportunities in this area. So first, what's machine learning as a service? And so the narrow definition you can find from the web is that for companies that provide machine learning tools as part of the cloud computing services, for example, AWS machine learning, Google machine learning cloud engine. But in this particular talk, I'm going to focus on a more general definition for this, which is we assume for companies that design or customize machine learning models to continuously serve their clients can be considered as a machine learning as a service. And so here is what we usually do for what we have already learned for machine learning as a service. Let me see. Can I'd like to share another file, which is the new one. Sorry about it. Okay. Yeah. So we all know that machine learning life cycle. So people start from gathering data and then prepare data, analyze them, and then we start to train the model, test the model, and then we deploy a model. So this is what people believe to be a life cycle for machine learning. And in order to train the model, we probably have to get a bunch of training data, and we have to know in advance what's the evaluation metrics, for example, accuracy, and we have to gather a set of testing data to evaluate the performance. And we normally are provided a deadline of completion, so we need to finish everything before a specific time. And there is a goal trying to build a model that can minimize the error or maximize some sort of accuracy. And this is what we have learned from school or from machine learning competitions. However, in order to use this machine model to build a machine learning service, there's a lot of things we have to do other than that. So here we can treat this machine learning life cycle as described previously as only one component in the whole ecosystem. So once we have this model deployed, then we have to continuously monitoring the performance, evaluate the performance, and then we have to during the surveying process, we need to collect the user's feedback or the user's outputs toward the decisions the machine learning model made. And those feedbacks can then be fed back to a system to further refine the machine learning model. And in this process, a lot of challenge can happen. For example, new concepts can come in, and that's called concept drift. Or there could be some failure opportunities, failure chance for the models, which can cause problems as well. And so we will go back to this later on. And furthermore, so for a company that use machine learning as a service or deploy machine learning as a service, usually they serve a lot of customers. For example, in Appier, we are serving hundreds or even thousands of customers. And because of the privacy of the data, usually we need to train one single model for each individual customer, at least one single model. So that makes the previous ecosystem or previous cycle I have described, we have to repeat that for hundreds or even thousands of times. So that can cause a lot of burden on the machine learning modeling engineer. So I will go back to that later on, and then let's first talk about the first part of machine learning service, which is the data acquisition. So several real-world challenges we have to face while building this, while trying to acquire data from our customers. First, the data sources can be imperfect, and the features can be missing, and the features can contain error, and the features can be free-format text and potentially very sparse. And to make things worse, and the labels we have obtained might not be perfect. So in real world, there could be inconsistent labels or missing labels. So on the right-hand side, it's an example. So this figure, I think it's a famous one can get from the internet. It depends on the structure of your brain. Some might interpret this figure as black and blue in terms of color, and the others can interpret this as golden and white. So this example tells us like different persons might provide diverse labels to our training data. And so below I list several state-of-the-art solutions one might want to check regarding to these issues. And in Appier, or in some machine learning service companies, we found even more serious problem in collecting data, which we believe is the bias that can be introduced through the data collection process. Below, I will introduce three very common bias we have faced. The first is the data biases from online serving. So usually, we are building a machine learning model, but the training data will collect from another model that's currently serving our customers. And for example, recommendation system. Okay, so say we want to build a new recommendation system, but we need another one or the old recommendation system to collect data for us. Say the previous system, they make some recommendation. In these examples, they decide to recommend this Harry Potter to the users, and the user would provide their feedback. Either they click or they purchase or they don't. But in this case, we obtain this feedback as the training data to train a new model. But in this survey process, the users never told us whether they enjoy the other movies or not, because those alternatives were not shown on the site to the users, so the users are not able to provide their feedback to us. So such bias is called the survey bias, and the data collected are biased given the online survey models. And the bad thing for this is that the model will eventually only recommend the existing products they have highly chance to be pushed by the previous model, and the co-star items will never have a chance to be evaluated, and so they won't get a chance to be pushed to the front end to be shown to the users. The second bias we call the manual labeling bias. So this is caused by the selections of labeling manual labeling process makes the distribution of the label data very different from the distribution of the overall data. So I will provide an example. Say if you want to use machine learning to build a URL detection model to detect malicious URL. And so people probably know that the VirusTotal is a database that we can obtain our training data. So in VirusTotal, people can submit suspicious URL to the site, and they will have experts in security to help us label those suspicious URLs. So some will be labeled as malicious and others will be labeled as benign. And so if we use this data to train a machine learning model, it will have some bias because this data never contains those trivial benign URLs. People won't ask VirusTotal if apple.com or facebook.com are malicious or not. And so this will turns out to be like the model cannot detect those trivial URLs as a good one. And to make things worse, there are like phishing URLs pretending to be those famous ones. So this could also lead the model to believe those famous links could be malicious. And the third type of bias comes from random sampling. So most of people believe random sampling should not contain bias, but the randomness in one dimension can lead to bias in other dimensions. So for example, if we want to build a machine learning model and we want to collect users' preference to train the model through online questionnaires, and then we all want to randomly pick online users as random as possible, but there are different ways to build to do this random process. One can randomly pick a set of online users on a given section, or one can, in advance, randomly sample a set of users in advance and then ask questions when they enter this particular website. So these two kinds of randomness will lead to different distributions on the training data, and eventually those models will be very different. So people might have heard about this Bertrand paradox. So this is a very famous one. Tells us, so this says that consider a equilateral triangle described in a circle. Suppose a chord of the circle is chosen at random. What's the probability that this chord is longer than the side of the triangles? And there are several different ways to define this random choose a chord, and depending on which type of randomness is picked, different answers, either 1/3 or 1/2 or 1/4, we will obtain different probabilities for this particular test. So this tells us like we have to carefully define randomness in order to avoid unwanted bias to the model. Then let's talk about evaluation. Okay, so to build a machine learning as a service, we have to inevitably face a problem that usually the ultimate goal our customer really wants doesn't 100% match the objective we are trying to optimize. So for example, in digital advertisement, eventually our customer want to know the purchase, want to increase the number of purchases. But because like we all know this marketing funnel, in this funnel, the click data are much easier to obtain than the viewing data, than the in-car data, than the purchasing data. So on the lower bottom of the funnel, those data are much sparse, which means machine learning might have to rely on the upper funnel, like click, to build this model but eventually want to evaluate the purchase. For example, in automated driving, eventually we want the auto car to realize the scenario. For example, is it safe to turn right or turn left? Should I keep going or should I stop? So those high-level decisions are more important for automated driving. But train a computer vision model for this driving, it's much easier to evaluate whether this model can detect the color, shape, or to recognize the objects correctly. So this also shows there's a gap between the trained computer vision model and the eventual usage scenario of this one. And for example, in AI dialogue system, ideally we want to understand the intent of this speech or of this dialogue. But to train the model, it's much easier to let model to optimize the word label accuracy or sentence label accuracy, because we have much more training data on that label. So how we can migrate this gap? So the model trained on this low-end goal can be adapted to be more flexible or to more adaptive to this high-level scenario is a very important task. If we want to serve our customer using a machine learning model, and also below I list several papers talking about this issue. And finally, as I have described previously, in machine learning as a service, this service never ends. So we have to keep serving for the customers 24 hours a day, 365 days per year. And in this case, there's no deadline for building model. The model has to, just like us training our kids, there's no end of learning. So we need to keep feeding information to them, and we hope they can keep improving themselves, and we hope they can adapt to a real world change through this whole process. So this also, furthermore, for machine learning as a service, we usually have to serve thousands of customers, a lot of them, and each of them have their own individual model. And those models, in order to be adaptive to the real world change, normally they have to be retrained every day or every week at least. Now, meaning that we need to train a lot of models on daily basis, and then the stability of the model is very important. So here I like to share 4 important key points to make this happen. First, the auto machine learning is important because we need to automate the whole training pipeline. And furthermore, we have to guarantee the chance this model can stop at a very bad local optimal is close to 0. And 99% is probably not good enough if we are going to serve thousands of customers. And also, we need to be aware of the concept drift, because things change every day. And if the model doesn't change accordingly, a serious problem will happen. Okay. Third, we need to synchronize the data acquisition and the model generation. So we know data keep coming, and we need to update the model continuously. And we want to make sure the new model actually utilize the most recent data to update the learning. And finally, we need to carefully monitor and also put alerts on some abnormal situations in order to guarantee the 24-hour performance of a machine learning model. And also, we want to be aware of the model complexity and quality trade-off. So here, building a machine learning model is not only about accuracy or performance. Although everybody spends a lot of time, we read a lot of papers trying to improve the accuracy, and probably most of paper focusing on that. but there are also computation costs to train this model. We have to consider, and more important, if we want to serve for thousands of customers, the maintenance and the serving efforts for machine learning model becomes very critical in this process. So for example, for retail or e-commerce customers, we know that the model accuracy might not be as important as providing real-time service or real-time recommendation to them. And so here we want to focus more on the serving side and focus and probably put less resource on fine-tuning and improving the accuracy of the model. On the other hand, for finance, and it's probably better to focus more on the accuracy because for finance prediction, large damage can cause by bad prediction. And so in this case, the real-time performance or the efficiency might not be as important. So here I'm only use one single page to describe Appier's solution to deploy machine learning as a service. So here we have spent a lot of time in data acquisition and pre-processing. In particular, we want to avoid the biases introduced in the process. Also, we have an auto ML process that do deep representation on the data first and explore the transfer or multi-test learning, try to make sure we can serve as many customers as possible, but we don't want to share data among different customers, so we need to be very aware of the privacy issue here. And once the model is deployed, we need to keep monitoring that, and we have to be aware of the concept drift and do a quick reaction. And given that happens, on the serving side, we need to feedback the feedbacks. We figure the user's response to the model, and through online banding learning to dynamically select model and ensemble different models to optimize the performance. Also, we need to consider lifelong learning to make sure the model can sustain in the long run. So the final remark is that we believe machine learning as a service is a very challenging mission and requires continuous investment of research and practical efforts to make it work. And it's very hard for students to study this topic at school because at school we normally do not build machine learning as a service at the lab. So that means having in-depth collaboration between industry and academia is essential to make significant contribution in this domain. And I will end my presentation here, and I believe we'll have about 5 minutes to answer questions from the audience. Thank you so much for listening. Okay, so let's see.